This is a revision video for P4h, nuclear power, chain reactions and nuclear fusion. First we're going to talk about nuclear fission. Nuclear fission is the splitting of an atomic nucleus. Not all atoms can undergo nuclear fission. Fissionable substances are those that can be split easily. To split an atom in nuclear fission, a nucleus must first absorb an extra neutron. The nucleus then splits into two smaller nuclei and releases more neutrons, either 2 or 3, and a massive amount of energy. Nuclear fission is the process which is used within nuclear power plants. The fuel is usually uranium or plutonium, and it's placed in the form of fuel rods within the reactor core. The reactor core is surrounded by thick concrete to prevent the release of any radiation. Within the core, there are also control rods, which are made from a substance which can absorb neutrons. When the material undergoes fission, it releases a lot of energy. This then goes through the heat exchanger, where it turns water into steam here. The steam is then released to turn a turbine, which turns a generator, which generates electricity. The most popular fuel for reactors is uranium-235. The uranium nucleus absorbs a neutron and splits into two smaller nuclei. This then releases 2 or 3 more fission neutrons. They then go in to hit other uranium atoms to make them fission as well. This is called a chain reaction. If this chain reaction gets out of control, then it can cause a core meltdown. We can prevent this from happening by using the control rods. If the core temperature becomes too high, we can lower the control rods down and they absorb some extra neutrons. Because these neutrons are being absorbed, they can no longer go on to make another uranium atom fission. So therefore, we are trying to control the amount of atoms that do fission, and therefore the amount of energy that is released. One problem with nuclear power is the radioactive waste and radioactive materials that can be made. When an atom splits as part of the fission process, it releases 2 or 3 extra neutrons. These are absorbed by other atoms in the materials that make up the nuclear reactor. Some of the new atoms that are created can be radioactive. Absorbing an extra neutron changes their nucleus and can make them unstable. This adds up onto the radioactive waste. Nuclear reactors can be found in other places as well, like on nuclear submarines and aircraft carriers. In nuclear power plants, the chain reaction is very carefully controlled. In the case of nuclear weapons, the chain reaction is left to go out of control. There's enough fissionable material that a huge amount of energy can be produced and released very, very quickly. This is what's used within a nuclear weapon. And this is why it's so dangerous, because of the very vast amounts of energy that is released at one time. Nuclear fission is a very, very important way of producing a lot of energy. However, there is an even more efficient process. This process is nuclear fusion. In nuclear fusion, nuclei are fused together or joined together to make a heavier nucleus. This is a process by which energy is released in stars. If we could do this on Earth, it would be even more important to us because the products of nuclear fusion are not radioactive. So unlike with nuclear fission, we wouldn't have a problem with radioactive waste. We have a problem with trying to do nuclear fusion on Earth. Atomic nuclei are positively charged, so when they come close together, they repel each other. In order to give them enough energy to overcome this repulsion, the nuclei must be moving very, very, very fast in order to get close enough to fuse. The only place where this can happen naturally is in the cores of stars, where the temperatures are extremely high. In the fusion process, we've got an atom of deuterium and an atom of hydrogen which fuse together to give us helium-3. Nuclear fusion would be very advantageous. It produces no carbon dioxide emissions like fossil fuels do, and it creates large amounts of energy with no harmful radioactive waste. The Sun's massive size and internal pressure is what creates the right conditions to do this, but trying to replicate that in a lab is very, very difficult. Scientists are making progress, however. There has been some developments in using strong magnetic fields or very high-powered lasers. But as of yet, no sustainable way of fusion has been found. For your exam, it's very important to remember the difference between fission and fusion. Fission is the splitting of atomic nuclei to form smaller nuclei and energy, and fusion is the joining or fusing of two nuclei to form a larger nucleus and energy. It's not just helium that can be made in fusion reactions. Every element has been created this way. The smallest stars only convert hydrogen to helium, but medium stars like our Sun convert hydrogen to helium, and then later in their life, the fusion of helium can take place to form elements like oxygen and carbon. Massive stars, later in their life, fuse nuclei to produce heavy elements. Elements that are larger than iron can be formed when large stars die and explode in supernova explosions. The origin of all the elements we have on Earth have been formed this way, even the ones that make up you. So we can say we are all made from stars. Okay, this brings an end to the revision video on P4h, nuclear power, chain reactions and nuclear fusion. If you scroll down now after the video, you can have a go at some of the exam questions which are underneath.